Yeah.
Yeah, okay. Yeah, so it's welcome everyone. So it's my pleasure to welcome Omri Azencot. We'll be talking about Koopman Approach to understanding sequence neural models. Thank you very much. Thank you.
Hi everyone, and thank you for the nice introduction. This is a work that was done jointly with my my student Ilan, yeah, and let's begin. Basically, the focus of this work is related to machine learning models, and in particular neural networks. And often these days, these type of networks are assumed to be black box models, in the sense that one can feed input to the model, and then they get output. And if the model like predicts, provides a good prediction, then everyone is happy. But if not, then it's not clear why. And even if the prediction is good, it's not clear what are the underlying mechanisms that actually drive the model to yield a particular observation or prediction. And this is a challenging problem that many people deal with in the last few years. And it gets more interest as time goes by, because these type of models are becoming more and more into production pipelines. So it's becoming crucial to actually understand what the network is doing, and not just having good accuracy or good classification results, or etc. etc. So just to give an example, that's a very basic example for the setup that we have in mind. Assume that you are given some review of a movie or a TV series, something like that. So this appears on the left of the slide. And then you feed it to the network, and the network outputs some classification. So this is a sentiment analysis problem. And the network may produce a number between 1 to 10, or maybe just provide like a binary sentiment, like a positive review or negative review, something like that. What we would like to do is to kind of open the black box and try to understand how it makes its decision specifically, and how it arrived to a certain result. That's a very general setup. I will, of course, try to make it more concrete in the following slides, but just as a setup, this is the general setup that we consider. Just a remark that I don't think I mentioned. Feel free to stop me at any point. I'm happy to elaborate or stop and answer to questions. I don't mind, and I actually prefer it, because then it becomes more of a discussion and not like a lecture or something like that. Okay, so let's see. The type of neural networks that we consider take the following form. In particular, F, the capital F, represents some nonlinear function. This is essentially the network. And the network takes inputs, which are denoted by X. And we are interested in sequential models. So all of the inputs that we consider have a time index related to them. So T, the subscript T is the index of time. And then we assume there is some inner representation that is associated with the network, which is represented by H. So H, I will sometimes call it state or latent variable. And then basically what the model is doing at each and every point is that it takes an input and the previous state, and then it produces the next state. Now, notice that in this particular equation, I don't even consider the output. I'm only interested in the inner representation of the network. And these are the models that we try to understand or explain. Many models fit into this particular setup, in particular recurrent neural networks and all of its derivatives like LSTM and GRU. Ecostate networks also fits into the description in some sense. And also networks that are not necessarily sequential, like residual networks. Under certain assumptions, they also fit into that description. So this is quite general. We mostly experimented with recurrent networks, but it would be definitely interesting to also consider like residual networks, but we didn't do this yet. So yeah, okay. Yeah, let's see. So to kind of set the scene to the method that we propose and what we have in mind, I will talk a bit about dynamical systems and then the Koopman viewpoint of dynamical systems. This may be known to most of the crowd, but in any case, just to be on the same page, I will try to go over this and yeah, and please stop me again if you have any questions. Yeah, so what I mean by dynamical systems in this particular context are time discrete dynamical systems, and they are autonomous in the sense that I have a state variable, which I call Z, and it have a time index, which is just an integer represented using K. And then my dynamics are given by phi, and typically we assume they are nonlinear in most interesting scenarios. And basically, this is like an evolution rule that pushes Z through time. So given ZK, I can push it through time using phi, and then I get the next one, and I can repeat it on and on. Just to make a small comment with respect to the neural networks that we consider, there it seems like we had something that resembles more of control. This is not really a constraint in that aspect, because in practice, what one can do is they can basically kind of concatenate. This is not from a theoretical point of view, just in practice, but they can concatenate the hidden state with the input, and then they can define an autonomous neural network in the same sense. So this is just a remark that basically, even though I showed neural networks that take inputs and also hidden state, they can be adapted to this particular autonomous setup. Yeah, okay, let's see. So yes, so ZR is the state, K is the index. And just to give an illustration, basically we assume to have some domain manifold represented by M, and you can assume that particles are running on this manifold, and they are pushed by this dynamics phi. Just to give two very basic standard examples, pendulum, that the motion of the pendulum is a very basic example that people typically use to kind of illustrate and show basic properties of dynamical systems. We, in addition to that, will try to take a more holistic sense of dynamical systems and consider also settings where it's not exactly clear that there is a dynamical system in place, in the sense that it's not clear that there are equations that govern the motion. So what you see to the right are the ECG signal, basically the electric activity of the heart. And at least to the best of my knowledge, it's not known if there are governing equations in the sense, or what are the actual dynamics. But regardless, we also consider these type of systems. So even though there might be a detachment from theory, we still consider this under the umbrella of dynamical systems. So these type of data and observations are definitely relevant in our setup. Right. Now, if we want to go now from the classical view of dynamical systems and move on to Koopman, there is basically an important change that instead of acting on state, so the equation that you see to the left is an equation that we had in the classical view of dynamical systems, and we discussed how a state at time k goes to the state at time k+1. What we have to the right is the Koopman view of dynamical systems, where now we have a Koopman operator, which we denote by capital K with a subscript of phi to remember that it is associated to a specific dynamics. And then it does not act on states anymore, but on scalar functions, f. Sometimes they are called observables. So f is a scalar function defined on the domain. And the definition of the Koopman operator is essentially by concatenation with the dynamics. And this is exactly the equation that you see on the slide. Essentially, to understand what the Koopman operator does to the observable f at state z of k, we pull back the information by concatenating with the dynamics. Just to give an illustration of what it might look like in a discrete setup. So imagine that we had this domain before. Now we sample it with a finite set of points, and we have our function f defined on these points. So the colors essentially represent some scalar function. Let's say that red are high values and blue are low values. And then what the Koopman operator essentially is doing is it is pushing the observable with respect to the dynamics. And that's essentially the difference between the classical view and Koopman view. Now, there is one important aspect that it is worth mentioning at this point. From a theoretical perspective, there is no loss of information for working with phi or having the Koopman operator, k of phi, in the sense that if I have phi, I can construct k of phi. This is, in some sense, the easy direction. But the other direction is also correct. If I'm given a Koopman operator, I can recover the dynamics. I prepared a basic kind of illustration that tries to capture the idea. This is, of course, not rigorous, but basically the proof for why you can recover from the Koopman operator the dynamics is essentially based on the idea that one can associate each point in the domain with a delta function that is defined on that point. And once you have this definition, this relation between these two, you can show that there is an homeomorphism between the domains. But basically, just to give an intuition for those who are less familiar with Koopman, just imagine that I generate a delta function. So now it's a discrete. So what you see on the slide is a cube. It's a rounded cube, and I define a function on that cube. So it lives on a curved surface, and this function is like a discrete delta or a smooth delta in the sense that black, the color black is related to 1, and then it diminishes like a Gaussian around that point. And let's say that I have the Koopman operator that represents the dynamics, and now I push this function, what you will see in practice is something like this. Yeah. And let's play it once more. Yeah, something like this. You will get you get a family of functions that change over time that shows how the functions changes. And I believe that many of you can agree that we have a sense of what the dynamics is doing, at least in the small neighborhood of that particular point that is centered at the Gaussian. Now, if we repeat this for each and every point of the domain, we will basically be able to recover the dynamics. And this is essentially the key idea behind how to prove that Koopman can recover the dynamics. Okay. Yes. So why Koopman is interesting, or at least why I in particular find it to be very useful in practice. This is I try to summarize this in this slide. Basically, the general assumption is that we typically consider that the dynamics is defined on a finite dimensional domain, but it is nonlinear. And having a nonlinear unknown dynamics is difficult. And we try to stay away from this. If we go to the Koopman setup, then the Koopman operator becomes infinite dimensional, but it is linear. It's kind of easy to show this. It's essentially based on the associative nature of composition of functions. But the key observation is that K is just an infinite dimensional matrix in some sense. And computing and processing and analyzing linear objects is of course simpler than the nonlinear case. And I believe this is like the main reason why people find the Koopman setup to be interesting, at least in the data-driven era. Now, of course, the problem is that the Koopman operator is infinite dimensional, and we need to kind of get around this. So I'll talk about this in a bit, but I just wanted to mention just briefly why the Koopman operator is infinite dimensional, because this is sometimes seems to be a point of confusion, or at least debatable. What I basically mean by that is that if I have a domain and this domain is continuous in the sense that the measure of it is non-countable, then essentially what I have with the Koopman operator is very similar to what people have with Fourier analysis. So what you see in this slide is that I have some signal, some red signal that changes over time, and then I can decompose it to what we call the Fourier modes or Fourier basis elements, and these are shown in the middle with the blue, purple, and pink colors, and essentially we have infinite amount of them. Yeah, every signal can be decomposed where the dictionary, the basis is infinite dimensional. With Koopman, we kind of have the same notion of infinity, in the sense that if you want to represent the space of functions on a domain, you will basically go back to functional analysis, and then you will say, okay, I need a basis to span the space of functions, and this will typically, for the domains I mentioned at the beginning, this basis will be infinite dimensional. Okay. Now I mentioned that the Koopman operator is infinite dimensional a couple of times, and then what do we do with this in practice? In practice, we need to approximate, of course, to be able to represent it using the computer. And the way that it is done, or at least the underlying assumptions that is common to most practitioners that work with Koopman is that we assume that most of the information that represent the dynamics can be captured in a finite dimensional matrix that I will call C. And then instead of trying to actually encode the infinite dimensional object, which is problematic in a computer, I will try to compute some matrix C with the hope that for my particular application, it is good enough. Yeah, so this is kind of the motivating idea. And there are a couple of examples where it works, and it works quite well. One such example is in graphics, computer graphics, and geometry processing. There, one of the main problems that people consider is the problem of matching or computing correspondences between shapes. So what you see here is essentially some person in two different poses, and let's say, and we only have the surface of these shapes. Yeah, only we don't have the inside, only the surface. And let's say that these surfaces are represented using point clouds or triangle meshes or something like that. And we don't know the relation between the point cloud on the left and the point cloud on the right. And we want to match between these two in the sense that we want to say how each and every point on the left is being matched to the point on the right. Now, in this particular example, since we have the same person, it is kind of intuitive and makes a lot of sense that there is such a correspondence. And it even should be like very nice correspondence because it should be isometric or quasi-isometric, right? If I only move my hands, I don't change the distances on my body, of course. Maybe there are some small stretches, but overall it should be very isometric. So it is kind of expected that we should be able to find the map between these two objects. In the last 10 years or so, Koopman-based approaches were developed in this field, and currently they are state-of-the-art for computing correspondences. There they call it functional maps. They don't call it Koopman, but it's essentially the same thing. Another such example is in nonlinear dynamics. There, it is mostly used for analysis of dynamical systems or data-driven analysis. But then again, there are many examples where it works kind of nicely. And one of the key examples that people show are this flow around the cylinder and its corresponding analysis. What my group and I are trying basically to do is to try to extend these type of successful stories into the more general domain of machine learning, where general data is considered like text or I don't know, general time series data that doesn't necessarily have a clear geometric features that one can learn. Okay, yeah. So this is just like a background information about dynamical systems in Koopman. What I would like to present now is the approach that we take to be able to explain and understand what neural networks are doing. This is essentially almost identical to DMD, dynamical decomposition. There are some general differences, but what we do in practice is very close to DMD. But regardless, let me try to go over the general procedure, and then we can talk about perhaps the differences between DMD and what we do. So basically, to make this entire idea of Koopman practical, there was this notion of applied Koopmanism that was turned by Budzik and Igor Mezik and others into 2012. But essentially, the idea is that we need to compute two things. Yeah. One is we typically need to reduce the dimensionality of the observations that we get. Okay, maybe let me, I jumped over myself. Let me first say what is the input. So typically the input to the problem is observables or discrete observables, yeah? This whole approach is data-driven. So what you see in F, the matrix F and G, these are matrices of observables, and the only assumptions that I have on F and G is that each column in F is or corresponds to the column in G with respect to the dynamics. So for instance, the first column in F is being passed on to the first column in G under the dynamics. And this is the only assumption that I have. So this is input and I cannot really change it. And then what I need to compute are, again, two components. One is the component that I denote by chi, and chi may serve different purposes depending on the particular setup, but typically what it is doing, it is reducing the dimensionality of F. And then it might also make the information in F to be more linear. This is more related to the recent advances in computing Koopman approaches that are using chi to be some nonlinear network. But this is essentially it. And then once we have that, so once we transformed F and we transform G using chi, then we can compute a linear transformation C, which will be representing the approximate Koopman operator. In terms of dimensions, F, we assume that it is M over N. Typically, M can be significantly larger than N, but not necessarily. It really depends on the setting. But the idea is that K, once you move using chi, you move to a different space, then the lowercase k is significantly smaller than N. So when you compute the matrix C, you get a linear system of equations, which is determined, or most often it is overdetermined. So you can solve it in a least square sense. Yeah. So the dimensions in M, the dimension M is typically the space. Yeah. Just consider the motion that we have in the cylinder, the fluid that goes past the cylinder, and then N is typically time. Yeah, so these are the observables that we collected over time, and K is some latent space that we compute. Okay, right, and what is the particular procedure that we take? We extract observations from the network. So just to recall again, I had a network F, neural network F, and it is computing an inner representation of my inputs, which I used H to represent. And I'm inputting to the system many batches, and I compute the observations or the hidden states of the network, and I collect all of them. So S represent a particular sample, T represents time, and basically I'm using my network to generate those. Then once I have this collection of hidden states, I choose a basis that spans the set of vectors or set of observations. Here the choice is kind of I have a lot of room and flexibility. What we do in practice is we simply use PCA. We simply compute the principal component of the matrix of the information that is encoded in H. but one can use other approaches, of course. And then we project each of the hidden states that we have into this B, this basis B. So I have basis elements Bj, and then when I project, I denote by H tilde J the coefficients of the projection. To find C, we simply compute a least squares between the coefficients in the basis. So you can see the tildes in the H's, and then I'm trying to find the best C that minimizes this error. This is essentially just a linear solve. So this is very easy to compute. Okay. Right. Yeah, so this is just a pseudocode. I don't think there is anything additional to what I described. I just mentioned here in step 3 that we take PCA or SVD of H. So here we take a particular choice, and then all the rest seems to be very similar. Okay. Yeah. Now. The final point that I wanted to mention before I move on to the results is that with this Koopman approach, even in the practical sense, it is sometimes useful, and we use it quite a bit to consider the eigen decomposition of C. Now, we always assume that C has an eigen decomposition, and this assumption kind of makes sense because it's really hard to not get such a matrix in practice. And even if you get one, you can shift it a bit, and then you get a matrix that does have an eigen decomposition. But essentially, since C is just a matrix, we assume that it has an eigen decomposition, and then with the eigen decomposition of C, one can represent the trajectories of the hidden states in a very natural form. This is the derivation of that, but basically the idea is that if you use the eigen decomposition of C, stuff cancel, and then what you get is that in the basis of the eigenfunctions of C, the dynamics become separable. The matrix become diagonal. And this is very useful, especially if you want to explore and study particular aspects of your dynamics. So this is a very useful feature, and as I said, we used it quite a bit. Okay, I think, do you have anything else? Okay, yeah, I wanted to mention previous work, but before I move to that, any questions up to now? I'll be happy to answer questions if there are any. Okay. Right. So let me briefly describe what people did in the past in the context of understanding neural networks. And there is a nice work from 2013 which only recently found applications, or at least more concrete applications, and it is based on the analysis of fixed points. So basically what they do is they say, yeah, okay, I have this network, this neural network F, and what I would like to do is only study the dynamics in the regime of points which are fixed under this neural network. So basically, the H star and X star are considered to be fixed points, and I'm trying to find a set of points that are fixed under the dynamics. And they typically fix X to be the input to be something specific, like 0, like a vector of zeros. And then they run some procedure, basically the network, to make it converge to find a set of fixed points. And then once they have the set of fixed points, they try to study the dynamics in the neighborhood of the fixed points using the Jacobians of the, specifically if you consider a recurrent network, then you have a Jacobian for the recurrent part, and then you have a Jacobian for the input part. And this is basically what they have been doing. Do you have another slide on this? Yeah. These are some results from a recent paper where they study the problem of sentiment analysis. Essentially, what they show, and this is visualized here in the middle figure. Basically, what they discover is that the dynamics of the sentiment analysis network is essentially a line attractor, where if you move to one side, then the network will say that the review is negative, and if you go to the other side, the network will say that the review is positive. This makes a lot of sense because by the end of the day, this network is just a binary classification machine, and it kind of makes sense that you have the decision boundary splitting the domain into two, although it doesn't have to be this way. Even in binary classification problems, there might be setups that are more complicated by that. But in any case, they obtain it from their analysis of fixed points kind of nicely. So this is the result, or at least the main result that they show in their paper. What we do is we kind of generalize it and extend it a bit further, and I will try to discuss this. People write some stuff. You said you use PCA for the basis for expression. In a lot of examples, the eigenfunctions of K are the most natural. You said, are you only advancing the dynamics? I'm reading from the chat. Just a second. So the question is, are you only advancing the dynamics using the basis of eigenfunctions, or do you ever represent H in this basis as well? Am I misunderstanding? So yeah, I might not have been totally clear with respect to this point. So the way that we compute, so we use PCA to essentially reduce the dimensionality of the hidden states. Sometimes people use a hidden state of size which is very large, like 1,000 or 500, something like that. And then you sometimes you don't have enough observations. So this will make the computation, the least squares, to be underdetermined. So PCA serves two purposes. It reduces the dimensionality, and then it gives some multiscale or hierarchical notion to the data. I mentioned the Koopman eigenfunctions because then in the analysis, and this is what I will show in the results, what we discovered is that PCA is not that expressed, is not really associated with the dynamics, and the Koopman eigenfunctions are related to the dynamics. So it is much more fruitful to actually study the eigenfunctions and try to infer what the network is doing from the eigenfunctions of the Koopman operator than to try to use the PCA components. I don't know if I answered the question. Yeah. Okay, perfect. Right. Okay, so some results that we had, and the first thing that we try to do is we try to understand whether the Koopman operator, the approximate Koopman operator that we compute, is it really even associated to the dynamics that the network represents? Let me maybe phrase it a bit differently. What we were trying to measure quantitatively is, let's say that you take an input and push it through the network. Now we have the matrix C that kind of replaces the network in some sense. Do we get the same results using pushing the input with the metric C in comparison to what the network is producing? And the answer is yes. Basically, what you see to the left is in the task of sentiment analysis. We computed. We take many batches of information. Some of the reviews are positive. Some of the reviews are negative. We have more than 99% agreement with what the network is producing for both the positive and negative reviews. So for the sentiment analysis, we almost had a perfect agreement. We also consider ECG classification. There, the results were somewhat not as good, but the task is more complicated. I will explain it in a bit. But basically, what you see here is that if the network produces a certain loss, so what you see in the graph to the right, you see the distribution of loss for all the batches that we have in the data. And the network is producing the histogram, the blue histogram. We basically push the data again, but now we use the metric C to push it through the dynamics. And then we compute again the loss, and we get a shift a bit, and also the maximum of the distribution is somewhat lower, but this is very close. So we were kind of happy with this in the sense that we believe that the matrix does encode at least the dominant aspects of the dynamic of the network. Okay. Yeah, now let me describe the tasks that we consider. The first one is the sentiment analysis task, which I briefly described at the beginning. Basically, the problem is that one is given text that represents reviews, and the goal of the network is to say, so this is binary classification, to say whether the review is positive or negative. The result that we had with respect to this extends the result of what I showed before to the case of n-grams. So what they showed in previous work is that they consider 1 gram, in the sense that they showed that the network is kind of counting positive words versus negative words. If the network sees enough positive words, then it goes in the line attractor towards the positive decision. And also in the opposite way, if it sees enough negative words. What we show, or what we are able to show with the machinery that I showed before, is that we can actually highlight what the network thinks of each and every input, and how it affects the decision. So what you see in the slide, let's focus, for instance, on the first bit. So this is a review that the network thinks is positive. That's why I use the blue color for it. And basically with our machinery, what we discover is that when the network sees certain positive words, it kind of highlights them. What does it mean? So basically, this computation is done by taking the batch, taking all of its hidden states, and then computing the matrix C, as I described before. And then what you see here is only the norm of the coefficients of a very particular eigenfunction. This is essentially the most dominant eigenfunction of the Koopman matrix. So essentially, what we discovered is that the most dominant eigenfunction of the Koopman operator, its role or purpose is to kind of track positive words. And the way that we visualize it is that we take the hidden states, we project them onto the eigenvector, and then we take the norm of the coefficients. And this has the key feature that it naturally highlights positive words. Now, you can probably notice that there are some positive words that were not highlighted. For instance, there is another good in this review that was not highlighted. This is okay. I mean, in some sense, we don't have any guarantee that it will highlight all words. What we do observe is that the network kind of aggregate the information as it reads the review. But this behavior was typical for many reviews. We see that the first eigenvector captures the positive words. The second example is for a negative review, and then we discovered that there is another eigenfunction, basically the second one, which tracks negative words. And again, we did the exact same thing, and we get an highlighting of the words mess and waste and muddled. Here, the behavior is a bit different because here we see that there is an increase in the value as you go along, and you also see that this increase does not diminishes at some point. This is basically because the network at some point kind of decided that this is a very negative review, and it did not see any positive information after that, so it just stays negative. The last example in the slide is considering the case of 2 grams. Yeah, basically phrases that are composed of 2 words, and then we again find eigenfunctions that capturing the information in those phrases. So if you have not bad, right? If I only look at the first eigenvector, or sorry, the second one, it will probably highlight the bad because it doesn't have the capability, or at least we didn't observe that it captures the not in this phrase. So it only captures the negative words. But other eigenvectors actually capture the 2 grams. And you can see that we have not bad and terribly wrong in the other example. So this is what we get from these eigenvectors. And actually, this idea generalizes. So at some point, it's hard to generate data that makes sense with general n grams, but we repeat this experiment with 3 grams. So this is what you see here, and then again we get the same observation, and we observe that there is some eigenvector that its purpose is to keep track of 3 grams. So in some sense, what the network is doing is it builds some hierarchy of n grams, where the most important are the 1 grams, and then 2 grams, and then the 3 grams, and so on. And it builds or aggregates information as it processes the input. Okay, so this is what we had on this example. The second example is a bit different because it deals with ECG classification. And while this is still a classification problem, the way that it is being solved is completely different to what we had before. Let me try to explain. So the way that people solve ECG classification these days is that they design an autoencoder. An autoencoder is a network that takes an input and needs to output exactly what it saw. The way to kind of avoid trivial solution like the identity function is to make the network shrink the data. So you have some kind of bottleneck at the middle, and then you avoid the identity function. So this is in general an autoencoder, and ECG classification is solved by training an autoencoder on normal beat signals, and then during inference, yeah, after you train the network, to classify which signal is normal and which signal is not, you basically run them through the network, obtain the reconstruction of the signal using the autoencoder, and then you compute the loss. Since the network was trained only on normal signals, you expect that the loss for normal signals will be low. So you can see here, for instance, that the reconstruction of the normal signal was quite good. It smoothed a bit the small variations in the data, but overall it captures the main behavior of the signal. And you can see this for all the normal examples that I show above. However, if you have an anomalous signal, then the reconstruction provides a loss which is not that good. So you can see here that the values are significantly higher. So basically what people do is that they have a validation set, and on that validation set, they try to find a threshold of the loss, where from that point, all of the signals are considered anomalous, and if the loss is lesser than the threshold, then the signal is considered normal. So basically, it's a classification problem, but it is solved as a regression problem, because the underlying network is actually it's an autoencoder, so it actually produces a smooth signal and not just a vector of probabilities. Okay, yeah. So what are the results that we obtain in this case? So what we observed is that the eigenfunction of the Koopman operator capture the main features of the signal with respect to, let's call it the salient features of the beat signal. What do I mean by that? So basically what you see, for instance, on the top left panel is that we have some signal in purple. You don't see it because it is covered by its reconstruction, which is shown with the blue color. So blue is essentially the reconstruction of the signal. And then we take the signal and its hidden states, compute the Koopman matrix, compute the Eigen decomposition of it, and then there is an eigenvector, or actually a pair of eigenvectors, 58 and 59, which seem to be capturing exactly the first minima in the signal. So this is what I denote here by the by this black dashed line, and this goes on for the other eigenvectors as well. So for instance, the pair of eigenvectors here, they seem to be capturing exactly this area that is spanned between, I think, time 35 and time 70, something like that. And then I have another pair that captures this peak, and then another pair, and so on. Now, probably this result might seem weird, because for people that are used to be working with SVD and PCA, this is kind of expected from a PCA point of view, right? If I have the data collection and I compute the principal components, I should be able to capture the dominant features of the signal. But one thing which is important to remember here is that we compute this entire information in the latent space. So this is not computed on the signals themselves. This is exactly what the network is trying to capture. And basically, by doing this, we get to the understanding that the network is trying to capture the dominant components of the signal. And moreover, if I repeat this experiment, but now I compute the PCA or the kernel PCA, this is just a different method, I don't get the same results that I had with my Koopman eigenvectors. So what you see with the other lines, which are not solid, you see that that I get with PCA and kernel PCA, you see that I'm not really able to capture the dominant features of the signals. Right. So this is the result that that we get from the ECG classification. Let me go over now. I consider to show another example, but let me skip this and basically go to the summary. So essentially, this work was dealing with representing dynamical systems, basically using Koopman operators. We are, of course, not the first one to do this, but this is the best of our knowledge. We're the first ones that try to do this in the context of neural networks and trying to understand what the network is doing. So essentially trying to learn the latent space of the network. What is nice about the setup is that the operators are linear and they are linked to theory and practice. So in some sense, the theory of Koopman operators and also the practice are advancing, are still advancing and are still in study. Our results show that this setup is instrumental in analyzing sequential neural models. We have a technical report that is given in the link below. And what we want to do for future work is try to study what happens to the network during training. So basically, this whole setup that we considered here was only done after the training of the network. So the Koopman operator was computed when the network is fixed and not training anymore. By the same idea, you could also do the same and compute a family of Koopman operators during training and try to gather information about how the network is actually trained when you get to overfitting issues or stuff like that. There is a question. So neural network training is affected by sampling. Have you studied the effect of mini batch sampling versus full batch? We did not consider full batch. So all of the results are with a particular batch in mind. So I extract a batch and I extract its hidden states, and then I compute a particular Koopman operator for that batch. I believe that if you take a full batch, then it might be problematic in terms of the results because the data sets that we have here are quite large, and it's not really reasonable to be assuming that a small matrix will be able to span the dynamics of all of the data. So in that sense, mini batches are actually helpful to our codes. So we did not consider this this aspect. Do the weights? So there is another question. Do the weights coefficients modes for each eigenfunction change with training? Like if you train longer on more text, does the okay? So this is the question. This is a question that we already started working on the aspect of training. Basically, the question is, what happens to the Koopman operator during training? Does it change significantly, or is there any change? Basically, what we see is that there is like an unclear regime that we don't really understand at the beginning, where the Koopman operator changes quite a bit. And then after some point, it stabilizes significantly, and then the changes are significantly smaller. So there is a clear point where after that point, the Koopman operator might change a bit, but basically the observations and the knowledge that you can gain from that operator is roughly the same. Let's see another question. Related question: is there a clear relationship, linear command between the nodes and weights of the neural node and the Koopman? is there a clear relationship between the nodes and weights of the neural network and the Koopman decomposition? I don't know. I mean, the networks that we take are nonlinear in general, and they may take all sorts of constructions. We never really tried to study the weights themselves. Basically, the weights are like, you know, tens of thousands or even more than that. So, and there is no clear way, or at least for us, how to study them. So I know that there is a group at UC Santa Barbara that tried to study the evolution of the weights using Koopman operators, but they are interested more in pruning neural networks. I don't know if they try to analyze the dynamics, so I can speak about that, but we did not consider this point. Okay, there is another guy. I assume the extracted Koopman operators may potentially be used to determine optimal batch sizes. Yeah, so this is definitely interesting. Can we, like the general question, can one tune the hyperparameter of the networks using the Koopman operators? I believe that this is really related to what we thought to be doing in the future work. When we wanted to study the family of Koopman operators that one generates during training. And basically the idea is that perhaps one might be able to actually identify how to tune certain hyperparameters like the learning rate, or if you go to, as I said, cases where you need to stop training, early stopping, and so on and so forth. So this is definitely interesting. I don't really have, you know, concrete answers to these type of questions right now, but it's a definitely interesting, you know, point to consider. Yeah. So I don't think there are any additional questions. These are my details below. I'm happy to chat if someone wanted to stay further, and happy to answer any questions. Thank you all for attending.
Yeah, thank you very much. And, yeah, thank you. Thanks for the next part. Yeah.
Yeah.
Yeah. Any other questions or last minute comments or? Yeah. Okay. Seems like you answered all the questions. Yeah. Thank you very much. Thanks again. Thank you.
Okay.
Yeah. Thank you.
Thank
Have
you,
a good
guys.
day. Thanks. Bye bye. Bye. Bye everyone. Yeah.
Bye.